Okay, one thing I want to show you before I jump into any material. Okay. I heard myself echoing, so okay. On the Canvas homepage, I have here the practice test one and its solution. So this is what I'll be talking about in class on Monday. Now today is the last day of any new material that will be on the test. And if I take a look at what's going on with assignments, okay, I see a number of you, but still not very many have turned in the next homework. So I will be sure to have that graded. So anything you get to me over a weekend, I'll grade that. And if I look at upcoming assignments, okay, so we have a homework that's due this coming Monday. I will do my best to get the grade those as quickly as possible. So for the practice test, it's kind of formatted as if it was a test I was giving in class because I was too lazy to change the format. But basically what you'd be doing is uploading your solutions like you do for homework to Canvas. And as long as I clearly identify, like, okay, this is problem 1, problem 2, etc. There are a total of 7 problems. If you are taking Math 417, so for you're an undergrad, you can just pick 6 of a 7 to do. Or if you are in 517, you're a graduate student, then you must work all 7. And then whichever set you're in, the problems will be weighted equally. Okay. So take a look at that as soon as you can. Let me know if you have any questions about the solution, but or bring your questions about that for Monday, because Monday is just going to be review. Okay. So now we'll get through the last new stuff, because I talked about the Fourier transform on Monday, and now we're going to see how we actually use it to solve PDEs that are defined on the entire real number line. But first, here's some properties of a Fourier transform that will help us do that. Okay. First, we have the this right here, where we compute this integral of a given function little f. This gives us the Fourier transform. So this is equal to, so here with this integral of a parameter c, or squiggly, gives us Fourier transform capital F of squiggly. That's a transform of little f of x. So then if you compute the Fourier transform of your function little f to get big F, and then you compute the inverse Fourier transform of big F, which is right here, that brings you back to little f. So the Fourier transform and inverse Fourier transform will have the effect of undoing each other. And that's something we keep in mind where we use this to solve PDEs, because what we do is we first compute the Fourier transform of a solution, because that's easier to get, and then take the inverse of it, and that will bring us back to the solution u of xt. Fourier transform is linear simply because it's defined as an integral, and integrals are linear. So what does that mean? If oops, typo, that should be a G. So for instance, the Fourier transform of a sum is the sum of a transforms. If you multiply a function by a constant factor, then that multiplies the transform by that same factor. So if you have a function like this, you can break it down into these individual transforms, so to keep things a little less cluttered. And the same thing applies to the inverse transform, also defined as an integral, so that has the same linearity. Okay. One of the pretty much the main reason that Fourier transforms are of interest for PDEs is because it's easy to transform derivatives. Okay. So here I have a transform of f prime, and I want to express that in terms of a transform of f. So the definition of Fourier transform gives me this. But now I perform integration by parts, where this is the u and this is the dv in the integration by parts formula. So now I have this boundary term, and then integration by parts formula gives me this integral. Now, this is the Fourier transform of just f instead of f prime, because those are exactly the same, except for f versus f prime. Now, what about these boundary terms? Well, to have a function that's Fourier transformable, it can't just be any old function. It has to be one that can be integrated on the entire real number line. Therefore, as x goes to plus or minus infinity, f of x must be going to 0. So, well, that was really weird to hear me echo like that. Okay. So this boundary term will go to 0. So what you're left with is okay. Something's off here. Okay, this should be a plus. Because the integration by parts formula has a minus. But I take the derivative of this with respect to x, and that causes multiplication by minus I squiggly. Therefore, the minus from the integration by parts formula becomes a plus. So that should be a plus. Okay. All right. So this is what we get, that the transform of the derivative is equal to I times xc, or I times squiggly, times the transform of the original function. So that's for first derivative. So now what if I have second derivative? Well, I just apply this twice. So Fourier transform of uxx would be equal to ixc whole thing squared times the transform of u. But I squared is -1, so we get minus xc squared. So this is very helpful for transforming like the heat equation, where we have uxx, it goes over to minus squiggly squared times transform of u. Someone have a question?
Sorry, my laptop's being weird.
Oh, okay. Good to know. All right. So that's differentiation in respect to x when the Fourier transform is applied to functions of x. What about with respect to t? That's actually more straightforward because we're transforming an x, not t. So differentiation in respect to any variable other than x, it just passes through. So in other words, the transform of a derivative is a derivative of a transform with respect to time. So if it doesn't involve x, then we have you can transform or differentiate in either order. So these two rules together show us how the heat equation can be transformed. You would get this on the left side, and you would get this on the right side. And I'll be doing an example of that a little later. Now, next property. Now, a transform of a sum is a sum of a transforms. That does not apply to products. We have a different rule for that. Okay, so what I'm doing here is I have two transforms multiplied together. And then I'm taking an inverse transform of the whole thing. So I want to show you how that works out in terms of the definitions. So here, this is the definition of inverse Fourier transform. And then capital F is a transform of little f. Capital G is a transform of little g. So now I'm going to work this out. So what I'm going to do is I'm going to take capital G and write it using the definition of Fourier transform. So this is the Fourier transform of little g. So then I can do some manipulations with these integrals. So what I've done here is I've switched the order of integration. So the integral with respect to x is now inside, and then the one with respect to y is outside, and I've moved things around accordingly. But then what I've also done is I've taken these two exponentials and put them together. So that's how we have e to the ix times x minus y. But dang it. Okay. But this is the inverse transform of capital F. Now, here's where we have to be careful, because if I look at the definition of inverse Fourier transform, that's up here. Now, notice here I have e to the ix x, and the result of its inverse transform is little f of x. So whatever's multiplying the ix, that's what your function is evaluated at. These two have to match. X here, x here. So now if I use that down below, here I have the same thing, except it's x minus y. Therefore, when I take the inverse transform here, I will get little f of x minus y. So that's what we have here, that we have this integral of f of x minus y times g of y with respect to y, where you can think of x as being a parameter. So this is called the convolution of f and g. So that's what the definition of this operation. So since this inverse transform of this product gave me the convolution, what I can do is I can now take the transform of both sides of this equation, and that gives me this, that the Fourier transform of a convolution equals a product of the transforms. And it goes both ways. The Fourier transform of a product is a convolution of a transforms. We won't really need that property, but this one will be quite useful to us for solving PDEs. Because what's going to happen is you take the transform of your PDE and then get a simpler equation like an ODE to solve. And often when you solve that ODE, to get a transform of your solution, it's often a product of functions for which the transforms are known. So then you have to use this property to go back and recover the solution u of xt. I'm going to show an example involving convolution. So here are my functions: f of x is x, g of x is e to the minus x squared. then turns out that the convolution of these two is, here we have a definition of convolution that comes from here. So f of x is x, so I get x minus y here. And then I have g of x, it becomes g of y, so I have e to the minus y squared. Now, I want to show you how this integral ends up being reduced to this one. Okay, I'm going to throw in a intermediate step here. Actually, okay. All right, so I'll copy the integral from here. All right. Now, if I break this up into two integrals, by distributing e to the minus y squared for the x minus y. All right, so in the first one, I'll have x. And in the second one, I'll just have y. Okay. Now I'm integrating with respect to y. That means x is treated as a constant. So in this first integral, pull the x out. Then we have this. This integral is actually 0. Can anyone tell me why?
Does it have something to do with the gamma function?
No, it's actually something simpler than that. Well, okay, I won't rule that out, but again, it's not what I was looking for.
It's an odd function on a symmetric interval.
Yes, it's an odd function on a symmetric interval. So because e to the minus y squared, that's an even function, times an odd function is odd. Another way to see that is this integrand, this can actually be anti-differentiated. So the antiderivative of this function is minus 1/2 e to the minus y squared. Then you plug it in the end limits, let the limits go to infinity, and again you would get 0. So it just reduces to that, which is what I've used here. Okay, and it's a well-known fact that the integral of this Gaussian function from minus infinity to infinity happens to be the square root of pi. So then we just simplify as much as we can, and we get x over square root of 2. So in this case, it was possible to work out the convolution of these functions exactly. In general, you might have to leave it as an integral. So like if that comes up on a problem on a test, then I would tell you it's okay to leave the answer as an integral, because I wouldn't want you trying to evaluate an integral that was literally impossible to do. Okay. So it can be like, this is not something that can be anti-differentiated in the usual way. I actually prove when I teach multivariable calculus that this integral is equal to square root of pi. But I do it using a double integral in polar coordinates. So I can transform into something that can be integrated. Yeah. Now, so I want to show you how we use Fourier transforms to solve a PDE. Okay. So here we have heat equation, and here's our initial condition. Now this is defined on the whole real number line. So there's no boundary condition since we literally do not have a boundary. When we have this kind of problem, it's actually called a Cauchy problem. So that's for an initial value problem that's solved on the entire real number line. So what we do is we take a Fourier transform of both sides of a PDE and the initial condition. So basically, we're transforming everything. And what we get for a PDE, we just have a time derivative of capital U, which is of a Fourier transform of little u. And then we have, on the right side, we have alpha squared. And then the transform of uxx, as I mentioned earlier, is minus c squared times the transform of u. So this PDE becomes this ODE. This right here is why we like a Fourier transform, because it reduces a PDE to an ODE. Or at least, however many variables you have, a Fourier transform of one variable will strip that variable out. So at least either way, you get a simpler equation to solve. And then we transform both sides of the initial condition, and that gives us the initial condition for this ODE that has c as a parameter. So whatever function phi we have for the initial data, we have this capital phi as a transformed initial data. Now this is an ODE that we can solve. This is what you'll learn to solve in like your first ODE class. So it's your initial data, and then exponential of this constant times t. So this right here is the Fourier transform of your solution little u of xt. Okay. So what we have to do now is take the inverse transform of this to recover the solution little u of xt. So how does that work? All right, so that's good. So it's defined to be the inverse transform of capital U. So that would be inverse transform of this. But here we have the inverse transform of a product of transforms. So that's going to be, so the inverse transform of a product is the convolution of the individual inverse transforms. So we can go ahead and inverse transform both of these individually as long as we take a convolution of them. We don't just multiply them. So now we have to inverse transform both of these. This one is quick because 5xc is defined to be the transform of 5x. So that gives us this here. Now, going from here to here, this I need to do some explaining. And for this, I'm going to refer to something in the, it's actually in the textbook that you will find quite useful. Okay. All right. Oh, I happen to be on the correct page. At the back of a book, Appendix 1, we have a bunch of tables of transforms, and actually pretty much all these transforms except the last one we'll be using at some time or another in this class. So Fourier sine and cosine transforms, finite or infinite. So the first one for table A, that's the one we're dealing with now. To make this a little bigger, but the print is in this PDF is kind of hard to read, unfortunately. It's not a very high quality scan. Okay. So this is the Fourier transform and inverse transform that, actually, sorry, this is the Fourier transform, this is the inverse. So on the left column, we have functions of x, and in the right column, we have corresponding functions of omega. So here, this table is using omega as a Fourier transform variable, whereas I'm using xc or squiggly. So what you can do is after you take the transform of your PDE and you solve the ODE, whatever you get, you try to match it to something in this column of a table so that you can go here to get the corresponding function of x, and that's how you're carrying out the inverse transform. So what I need to do is look up in here for a Gaussian function. How do I transform a Gaussian function? So for that, I look here, and here I found what I need. But I want to take a little time, I certainly have the time, to work through the algebra to show how I use this to get what I need over here, like to go from here to here. Okay. Now, and once I have this, I have convolution. Here I'm just using the definition of convolution. This is as far as I can go. So I stop here. This is my solution. Unfortunately, it has to be left as an integral because phi of y could be anything. This is not given to me. So whatever initial data you have is what you put in here. Okay. So if I copy the transform that I need of a Gaussian function. All right, so what I have here is 1 over a square root of 2 times exponential of minus omega squared over 4a squared. Okay, so actually I need f inverse. All right, so the inverse transform of this function is equal to e to the minus a squared x squared. Okay. So this is what I need the Fourier transform of. But this is the Fourier transform formula that I have. Okay, I have some sort of LaTeX error somewhere. Oh, I see. All right. So I need to be able to use this to transform this function that's of a similar form, but not exactly the same. Okay. So what I need to do is I have some parameters here. Here I have omega and a. So if I can choose omega and a to make these match up somehow, or at least as much as possible, then I'm in good shape. Okay, so what I need is I want to match up the exponents. So I have alpha squared c squared t now to make the notation a little more uniform, here xc is what I'm using as a transform variable, but in the book they're using omega. So I'm just going to change omega to xc just to make those match. So now I can focus on matching up the constants. So I need alpha squared t. So for the rest of the exponent, I'm ignoring a minus c squared. That must be equal to what we have here. So 1 over 4a squared. So what I can do is I can use this equation to solve for my parameter A. So what I get is 4a squared is equal to 1 over alpha squared t. So so a turns out to be 1 over 2 alpha 2 alpha square root of t. Okay. All right, so now what I'll do is I'm going to take this formula with this value of a and fill that in. All right, so for a I have that. So I have okay. Okay. All right. So now if I clean this up as much as possible, so okay. All right. So when I square this, I'm going to have 1/4 and then alpha squared t. Well, the 4 and the 1/4 will cancel. All right, so then I'll just have alpha squared t. But that was actually in the denominator, as we can see here. So then I've minus xt squared over 1 over that. So this flips up to the numerator and gives me what I'm supposed to have as by design. So we have L squared xt squared t. Okay. And then if I sort this out, I have a square root of 2 here in the denominator, and then I have that divided by okay. So now I have that divided by 2. Okay, and then I also have alpha squared of t. Okay, so then if I move all that up to the numerator, okay, and then this will simplify, so I just have square root of 2 alpha square root of t. Okay. All right. Actually, I'll put the 2 and a t in under 1 square root. Okay. So, all right. But if I go ahead and square this and clean it up a little bit, so then I have x squared over 4 alpha squared t. Okay. Just from filling in what a is. So then the only other thing that's done up here is, here I did not have any constant in front of the exponential up here. But down here I have its constant, so I have to divide by that constant, and that's what leads to this fraction down here. Yeah. All right. So, so by matching what you have with whatever known transform formula you have, you can figure out what the inverse transform is supposed to be. Just by figuring out like a right value of whatever constant is in the formula from your table. Okay. So any questions on what happened here? Okay. All right. So, so then we're done. This is the solution in terms of a convolution. So, to understand the structure of a solution, notice that the solution u of xt is a convolution of your initial data with what's called a impulse response function or Green's function, that is this exponential. So one way to interpret the solution is if you take your initial data at y, then this expression here, multiplying by the exponential or Green's function, gives you the response at x to the impulse at y. But what that means, and then what you do is you take all of those responses, like you're taking the response at x to all the impulses, because you get a separate impulse for each y value. So now you take the response at x to all of those impulses, and effectively you're adding them up, which is what this integral is for. And that superposition of all of those responses to the stimulus for each y gives you the solution at that x. So that's just a perspective on how to understand the solution in terms of the initial data. So you can think of it as the initial temperature profile at any point y. How does that affect the temperature at some point x at a certain time t? This is how. And what that means physically is that the temperature later in time at a given location x is affected to at least some degree by the initial temperature everywhere. Now, if y is far away from x, then this exponential will turn out to be small, so it won't have very much of an effect, but there still is an effect. And what's also interesting is the effect is instantaneous. So for any t greater than 0, but there's some non-zero contribution to the solution at x from the initial data y. So it's like there's an instantaneous effect, which is very different from other phenomena that we'll see, where we have what's called like a finite speed of propagation. So when you have parabolic PDE, like the heat equation, you have what's called an infinite speed of propagation, that whatever happens at time 0 affects what happens at t greater than 0 everywhere immediately. Whereas with the hyperbolic equation, such as a wave equation, that's not true. That what happens there is what happens at a certain point y will not necessarily affect what's happening at x, especially if x is far away. It may take some time for that to happen before it manifests itself in the solution at x. That's a finite speed of propagation. So we have this fundamentally different behavior between solutions of PDEs of different types, so hyperbolic, parabolic, and also elliptic. And when we study the wave equation later, you'll get to see what those differences mean in terms of how the solution behaves. Okay. Now that's all the new stuff I have. So one of the problems on the practice test will be using these Fourier transform rules to be able to solve a PDE stemming from a heat equation. So it'd be a good idea to when you do problems of that kind from less than 12 to refer to this table or these Fourier transform tables, whichever transform is appropriate, to be able to take transforms or inverse transforms of whatever functions. Like if you're given a specific initial data, like your 5x, then you would look that up in this column to see if find a function that matches, to see what the transform is, to get the initial condition for your ODE. And then once you have a transform of your solution, you look that up and match it to something in this column to go back to get u of xt. Okay, so so do you have any questions about this or about ongoing homework? I've been a quiet bunch this week. I'm like, please don't ask a question. Please don't ask a question. Well, I hope you at least have questions on Monday, because that's about to test. Make sure that you understand what's in the practice test solution to help you be ready for real things. So at least from that, you'll see what types of problems you can expect on the real one. Okay, well, if you do have questions about these, be sure to contact me, and then we'll make sure on Monday that that everyone's ready for a test. So I'll stop recording here.